Okay, this is chapter 12, the first chapter for exam 5, and this is on sound. All right, and this will be related to lab 12, concepts in here with the standing waves in the sound tube. So, I'll go through this chapter now. All right, we talk about sound travels. We talk about air. It travels with a speed of 331 plus 0.6 times T in degrees Celsius. And at a room temperature of T equals 20 degrees Celsius, speed of sound is approximately 344 meters per second, or approximately 750 miles per hour, roughly. So that's the speed of sound as far as in air is concerned. All right, now that's just in air. In other materials, it's different. In helium, which is where you hear like sounding like Donald Duck, because it's so light, the speed of sound is approximately 1,000 meters per second. And in other materials, such as water, it's about 1,500 meters per second, and it's solid like steel, it's on the order of 5,000 meters per second, or 3 miles per second. There's a little video link I'll put on there on YouTube of comparing speed of sound in helium and also a very heavy material. I think it's called sodium hexafluoride. And this is a very dense material, very dense gas, and that what you sound deeper. So I have got a little video link on the chapter 12 parts related to that. So that's what we have there. We talk about sound waves. Particularly we'll talk a little bit here related to musical instruments, but for the most part, we're going to be using speed of sound is 344 meters per second, 750 miles per hour. So these are the numbers we're going to be using, assuming approximately room temperature. All right, a couple things here. We talk about musical pitch is related to frequency, and loudness is related to amplitude. The range of human hearing goes from approximately 20 hertz up to approximately 20,000 hertz, where this upper range generally decreases with age as far as that's concerned. So this is a little bit related to human hearing as far as these characteristics. Okay. So, related to that, sound is also, I should say, sound in air is a compression wave. Meaning the molecules vibrate back and forth in the same direction that's propagating for that to occur. So sound needs a medium to transmit through for it to propagate. That's why sound in a vacuum, such as in space, doesn't do anything, such as you might see on some Star Wars movie or something. When you see a big explosion, well, you wouldn't hear anything. It might be a pressure wave of the energy, but there's no sound related to that. Okay, so that's it there. So pitch, again, is related to frequency. Loudness is related to amplitude. So I'm going to move into now a little bit is section 12.2. Leave this up here for a minute. All right. So, moving on here. All right. We have intensity of sound. All right. Now, intensity is measured in watts per meter squared. So it's how much energy or how much power in a certain meter squared. Right. First of all, this density, this energy falls off with the square of the distance. Since we assume a sound wave going out symmetrically, intensity falls off with 1 over r squared. So as we double the distance, it's 1 over r squared, so it'll be 4 times less. 1/4 as much, I should say. All right. So the farther away, that's how it falls off there. Now, for a given distance, though, if we have 2 sound-producing things, such as an example might be someone talking. All right. They produce an intensity of approximately 3 times 10 to the minus 6th watts per meter squared. So it's relatively small. Then at the other end, you have, if you were to be close to a space shuttle launch, or whatever they had, space shuttle launch, all right, this can be the intensity on the order of 1,000,000 watts per meter squared. I mean, this would be a highly intensive, highly loud noise. This is why when they do the spatial, any launch, nobody's within 3 miles of the launch pad because the intense sound is so loud. So this is a huge range. This is 10 to the 12th times the range of that, and that's not even the lowest. The lowest person can have is what we call the threshold of hearing, and that's around 10 to the minus 12th watts per meter squared. So this is like 10 to the 18th or 10 to the 19th, approximately 18th that. So how do we deal with that, all right? Much like we have the earthquake scale where you have the earthquake scale, Richter scale, where a 7 is 10 times more intense than a 6, and so on, because it's a logarithmic scale. We do the same thing here, and we introduce the concept of decibel, right? Or dB for short, all right? And how this works, okay, is that we have this range, and I'll put it down, let's see, let's put it over here. Let's put it down here because I want to leave these up for a minute. A decibel sound is dB. I is 10 times the log of I over I naught, where I naught is the threshold of hearing, 10 to the minus 12 watts per meter squared. So what we do then, all right, okay, so we put in what this would mean then. So if we actually had the threshold of hearing, this would be 10 times the log of 10 to the minus 12th over 10 to the minus 12th, which is 10 times the log of 1, which is 0. So this we call the threshold of hearing is 0 dB, right? So the lowest we can hear is that. If we have something higher, let's do an example of someone talking. Okay. All right. So our 3 times, this would be dB, would be 10 times the log of 3 times 10 to the minus 6th over 10 to the minus 12th, which is 10. Take the log of this. This is base 10. This is 6.5. This is 65 dB. That would be for someone talking. For the space shuttle, we put in, you can try it yourself, space shuttle launch. All right. This turns out to be on the order of 190 dB. So very high. Table 12.2 has some other examples related to this as far as intensity and sound. So what we have here then, and we're not really going to be calculating it directly too much, but what we can do is compare. So what we have here then is based on this scale, if something is 10 times louder, it's going to be an increase of 10 dB. So every increase 10 times, factor of 10, increases by 10 dB. So, so this is someone talking. All right. So on this, as an example then, so we have someone talking. This is about 65 dB. So one person. That. Now let's say we have 10 people, 10 persons. All right? This is 10 times louder. So it's going to be 65 plus 10 is 75 dB. Right? Now if you have 100 people, this is 10 times 10. Each increase is 10 more, so it'll be 65 plus 10 plus 10, or 85 dB, and so on. So if you had 1,000 people, it'd be 95, and so on. So each increase of factor of 10 increases by 10 dB. So that's the decibel scale. That's more of what we're going to be looking at. But I gave you that formula for calculating dB in terms of threshold of hearing, which is 10 to the minus 12, and using the log scale. And for example, again, say log of, say, 1,000 over 10 is log of, oh, yeah, that would be, which would be 2. Okay. So 10 times that would be 20, right? So every factor of 10, you increase by a factor of 10, it increases by 10 dB. So that's the decibel scale there. And that's section 12.2. All right, moving on here. I'll leave this up for a minute. Okay. Moving on. All right, we're not going to get anything into the ear and its response and things like that. Oh, yeah, we'll get into vibrating strings. All right, so we did vibrating strings before, right? So the fundamental, so we did for lab 11 is, this is the length, L, the wavelength. Here we have L is lambda over 2. If we have one full wavelength, then lambda equals L. If we have 3, then lambda L is 3/2 lambda, and so on. So we have standing waves, and turns out then the fundamental, so we call this a fundamental frequency. Okay. So this will be the lowest this can vibrate at. So this is fundamental. All right, the next one is 2, and that would be then given by N times F1, N times F1, and so on. So if this is 100, vibrates at 100 hertz, this would be 200 hertz, 300 hertz, and so on. Okay? So that's what that would vibrate at as far as that is concerned. We've also talked about speed of sound. Again, speed is given by frequency times wavelength. So as the frequency goes up, the wavelength goes down. So that's what. So each of these are what we call harmonics of the fundamental. So these are harmonics of the fundamental frequency. All right. Now, I've shown this a little before, and I'm not going to get into too much as far as sketching, because this is really the basis of Lab 12, as we'll see. Lab 12 deals with not the vibrating string, but an air column. All right, we've had this before. where you take a column, a tube, certain length, put a resonant frequency in this end, and either have it open for an open tube or this end closed for a closed tube. Again, we don't close the other end. And what we have here are characteristics of open and closed tubes, and I'm just going to show that here as far as from the book, because we measure the pressure, and if you look at lab 12, these are the fundamental frequencies for our harmonics for an open tube, where because there's nothing at this end here, right, it's just nothing can hold the weight. It just air comes out. So and the pressure is what we measure with the microphone. We have a note at each end, and these are the certain harmonics of the closed tube. So for an open tube, for a closed tube, we cap the other end, and the sound can vibrate, can reflect off that, so we can have a maximum at this end. And in that case, we have what we have in the text, and again from lab 12, is these are the harmonics for a closed tube. And so how does that work then? So what we have these fundamental for vibrating string, 100, 200, 300. All right, if we look at for a tube then, right? I'll try to do it somewhat like they have it. This, that's okay. All right. So the open, and I'm just going to do the first 3, and for two closed, okay, for an open tube, we have this, and the next one is a full wave, so that's half a wave. And then, oops, too many. Oh, doesn't matter. I'll just do it inside. Let's just do it that way then. Then we have there. Okay. Here we have F1, fundamental frequency. Then F2 is 2 times F1, and F3 is 3 times F1. Right? So this is the fundamental. For a closed tube, right, we have a maximum at the closed end, and much like we have the open tube, it's going to be open at the place where the sound comes in. All right, this is actually going to be, this is L, and the wavelength is 4 times L. This is the fundamental then. Then for the next one, and I'll just do it the same way, just kind of have tubes, they're all connected. Then the next one will be this. Okay. And this next one is actually going to be the third harmonic. And then the next one is going to be the next one is going to be F5 is 5F1. So in the closed tube, we only have odd harmonics. And this one we have all. For the open tube, we have all harmonics. For the closed tube, we only have odd harmonics. So if this one is 100 hertz, then the next one will be 300, and the next one will be 500. So in a closed tube, we only get odd harmonics that will resonate in there. And so these are vibrating too, like it's if you had a pipe organ or any type of instrument like that. All right, related to this then is the question of, how do we have how do we have other kind of sounds produced? Open tube, closed tube. These are all harmonics. Now, if you start looking at section 12.5, which is on music quality of sound, then we start looking at, comparing a simple tuning fork. All right, this is a B, 480 hertz. All right, it's a nice simple sound, but this is just one frequency. And if we were to look at this, then the sound, if we look at it in terms of what we call the frequency spectrum, okay, this will be, this is section 12.5. If you look at the simple tuning fork, if you look at amplitude, and frequency in hertz, a simple tuning fork has a single frequency, in this case 480 hertz, and it has a nice simple sound to it. Now, if you compare that though to say a piano, a violin, a clarinet, something else that plays the same B, all right, then what you're going to get is, instead of a simple frequency, what you're going to get instead are harmonics. So if this is 480, but you're also going to get other harmonics such as 480. All these are multiples of the base frequency. So this would be 960. This would be 3 times that, which would be what? 1440, and so on. So you have a piano has harmonics that combine together in just the right frequency and amplitude to give that classic piano sound. The text shows it pretty well as far as that is concerned. As far as these higher harmonics, clarinet, piano, and violin, they're all harmonics of the fundamental frequency. So for a violin, you have the main harmonic, then you have decreasing harmonics. So these are all multiples of the fundamental, or a tuning fork could just have the one. So this would be for a violin, perhaps. And then that way, if we could reproduce these sounds exactly the same way in the same ratios and amplitudes, that's how a digital instrument works. It just reproduces it so it sounds like a piano, a violin, a clarinet, like a digital organ, digital instrument, keyboard. That's how they do that. So you have harmonics of the fundamental. And that's how you get the beautiful sounds for classical instruments. All right, so that's section 12.5. We'll move on to 12.6 here now. And this is the concept of beats. All right, so this is section 12.6. And concept of beats. Now, you ever heard of a classical orchestra? The first violin will play a A440, and then everybody tries to adjust their sound so they can be close to that. So how do you do that? Well, use the concept of beats, beat-frequency beats. And we'll give an example here of this using this function generator like we used for Lab 12 and for two different things. So I have it set at approximately 140 hertz. All right. So we get that sound 140 hertz. Now I'm going to do is play a second one. And it's much lower. Now, so this is A and this is B. Now, I got the top one, I'll leave that. Bottom one, I'm going to adjust. You can sort of see a beat pattern happening where it's getting louder and softer. And then as I get the two closer together, then they're the same, they sound like one sound. But if one's slightly off, you can hear it getting louder. So, or if I go a little bit above, so we start hearing the beat frequency. All right, enough of that. And so what we hear is this louder and softer sound, and this beat frequency is given by F1 minus F2 is the beat frequency. So if the two are exactly 140, then the difference is going to be 0. So 140 minus 140 is 0. But if one is, say, 140 and the other is 143, we'll hear a beat frequency of 3 hertz. Now, generally, we can hear a change up to about, say, 20 hertz. So if the difference is up to about 20, that's about the maximum, because then it's all sounds like one big, you can't hear that anymore. So it has to be within 0, the difference has to be about 0 to 20 hertz to be heard, to be detected. Okay, so that's about what you have to have for the limit there. And that's why when they have orchestra, they'll try to start tuning their own instrument so that you start hearing the beats minimized. When you hear them minimized to 0, then you're close. But you have to be relatively close to begin with. So that's what we call beat frequency, so if they're relatively close, that's what you get. So that's section 12.6. Then the last section I'm going to cover is the Doppler effect. So this is the beat frequency, right? And it has to be within about 20 hertz maximum difference for that to be heard. So if I had one to do this, if I had one that was 140 and one that was 200, you could not hear the difference. You could not hear that because the beat frequency would be 60, and that would be more than you could hear as far as our response. All right, so that's it for there. I'm going to cover the last section now. And that I'll be talking about, and that is the Doppler effect. And so can we do this? Can I make this work here? Yeah. So if I have a sound here, it's about 140 hertz, and I hold it steady, you hear that. Now, if I move it back and forth to you start hearing a change in pitch. As it's moving towards you, it gets higher. We'll get to that. And it moves away, it gets lower. And it's easier to detect as it goes back and forth because the chain can detect the change of pitch relatively easily. And that's what we call the Doppler effect. So what we see here is if we have a truck or something, a fire truck putting on a siren, right? And it's moving at a particular speed, V, then the waves as they're coming towards you are higher pitch, and as they're moving away, if you're over here, we have a lower pitch. And you detect it easily. The best is if it's coming to pass or it's moving back and forth like I just showed the demonstration. So say a fire engine, as it passes by you, it goes to, if you're standing right, as it passes by, just before it's higher pitch, just after it's a lower pitch, and you detect that change in pitch right there. So how we're going to do this is that look at cases where either this is the source moving or observer moving. All right, so either one or the other moving, and for that then, we're going to look at how does the pitch actually change. So I've got the expressions are in section 12.7. I'm I'm going to give them to you now, as far as those concerned. So I'll erase this. So, now first of all, it's not going to be a huge change. I mean, you're not going to have, say the frequency is 100 hertz. I mean, it's going to be on the change, is on the order of change on about $5 to 20% max, right? So it's not going to be doubling. So dealing with realistic sounds, because then the speed of sound, again, speed of sound is 344 meters per second, which is what we're going to be using. The S, and so we have is observer moving, so a truck is standing there and you're moving either towards it or away from it. F prime will be 1 plus V observer over V of sound times frequency. And if it's moving, so it's moving towards, and if it's away, F prime is going to be 1 minus V observer over V sound times speed of frequency, all right? Then if we have source moving, then towards, it'll be F prime will be F over 1 minus V source over V sound. And if it's moving away, it'll be F prime, I should put it up here. F prime is F over 1 plus V source over V sound. So you can see in this case, if it's moving towards you, this will be greater than 1, so it'll be an increase in frequency. In this case, we have minus, so it'll be less than 1, so it'll be a decrease in frequency. Here, if the source is moving, this is going to be less than 1, so since we're dividing F by a number less than 1, the frequency is going to be higher. And in this case, this will be a number less than 1 or greater than 1, so F divided by a number greater than 1 will be F prime. So these are the expressions we have. Either the observer is moving or the source is moving in this case. So I'll do one example here with the source moving either to or away for an example. So I'll leave those up in a minute. Those are in the section 12.7 as far as that's concerned. Okay. All right. Now I'll do an example of 100 hertz. So we have 100 hertz. Let's say the source is moving at, say, 30 meters per second, which is about 75 miles per hour. Okay. Okay. And in the first case, F prime will be 100 over 1 minus 30 over 344. And that would be, if you calculate this out, to be then 34. All right, so that's going to be 1 minus that. It is 100 over 0.91. We get approximately 110 hertz. Okay, so if it's moving towards you, that's going to be okay. Now if it's moving away, same thing, it'd be 100 over 1 plus 30 over 344, which would be 100 over 1 point. Okay. Which would be approximately 92 hertz. So if it's moving away, it would be about 100 hertz, 192 hertz, moving towards about 110. And you could detect it easily as it passes right by you, going 75 miles per hour. So that is the Doppler effect, as far as that's concerned. It's very famous. It was discovered in 1844 by Christian Doppler in Salzburg, Austria, which is actually a more famous town for the birthplace of Mozart. And that is all we have there. The last section, 12.8 on sonic booms, I got a couple of video links that I'll post related to that. That is all of chapter 12, right? So that is the first chapter for the last exam 5, which will start the